Hello, everyone. Welcome to our second presentation for Senior Project. This is a combined approach to motion recognition. We are the Mood Meter Maestros. I am Andres Martinez, the project manager.
I'm Manuel Nunez, the Scrum Master.
And I'm Jonathan Mesa, developer.
So we're going to start off with part one, which is a software demo and project walkthrough. So for this part, we're going to display various parts of our functionality that have been implemented thus far. We're going to start off with the exploratory data analysis. We're then going to move on to data preprocessing for both the audio and visual model. Then we're going to cover the architecture and training loops for each of the models. We're finally going to show a sample run using both models and user input. And then we're going to comment on how this user input is created in the first place by showcasing the user input program. However, before we dive into the live demo and walkthrough, we're first going to comment on the architecture of both models, starting with the visual model.
So we leveraged DenseNet 169, a deep convolutional network pre-trained on ImageNet to enhance feature recognition across diverse image datasets. After feature extraction, global average pooling, GAP, simplifies feature maps by condensing them into single values, reducing complexity significantly. We include dense layers with L2 regularization to prevent overfitting, encouraging the model to identify simpler and more broadly across applicable patterns. So dropout layers between dense layers deactivate random input units during training, preventing reliance on single nodes and averting overfitting. Finally, a dense layer with softmax activation provides probability distributions across multiple classes, ideal for diverse classification tasks.
So for the audio model architecture, it is also convolutional neural network is applying to the MEL spectrograms of the audio. The data first passes through a convolutional layer, which slides through the whole image, applying a kernel that will maximize the features within the image. After each convolutional layer, the data passes through a pooling layer, such as max pooling or adaptive pooling, which are both used in our audio model. This reduces the size of the data while keeping the features highlighted. Then after going through a few of those, they go through some fully connected layers, which resemble a traditional neural network with nodes and activation functions, finally classifying the data into one of our 8 classes that it was trained into.
Great. So now that we're done with architectures, we're going to hop right into the live coding demo and walkthrough, starting with the exploratory data analysis.
So this is the exploratory data analysis for faces and for images. I'm going to kind of gloss through it because we covered this in our previous one. We load in the data, look at the counts of each. There are imbalances, which we do account for. And yeah, so moving on to the preprocessing, this is the audio data preprocessing. First, we read in the audio data and load its waveform. From there, we need to get the spectrogram from this waveform. And then finally, from the spectrogram, we load the MEL spectrogram, which is the optimal way to pass audio data into a convolutional neural network. I used a dataset class, which is pretty standard, and train loaders. This is my preprocessing pipeline, which applies MEL spectrograms to the audio data, drops the other data columns from our training data that was not super relevant, and splits it into testing and training data for the model. From there, this is the model as described earlier with several convolutional layers, max pooling and adaptive pooling layers, which are applied to the convolutional layers as well, and linear layers that fully derive the 8 output classes as described earlier. And our forward pass of the function, which implements each of these layers at least once. And this is our training loop, which uses the train loader and passes the data into the model. We have CUDA implementation, which I do not have in my computer, but we will touch upon that later. And yeah, this is the result of several epochs of training. It is not too much training because we are waiting until we have the optimal hyperparameters to train on that CUDA device. This is the evaluation. And then here's a sort of demo we have with a short recording that we have made. This is a recording of Manuel looking angry. So we are looking and sounding angry. So I read in the WAV file, I plot the waveform, and then from there, I just pass it, I pre-process it, like I mentioned earlier, and pass it through the model. And here we have the output probabilities. And based on this, you can tell that the model is not perfect, and there still is work to be done, but it is a good start. From here, we will transfer over to the facial model.
So we're going to start off with the data preprocessing for the facial model. The first thing we had to do was read in the CSV file, which contained all the data pertinent to facial recognition. We split this data into 3 respective files, one for training, one for testing, and one for data validation. However, before any of this, we first in other words, we outputted the number of samples that existed for each label. We saw that they weren't evenly distributed. So we had to upsample minority classes and downsample majority classes, such that we ultimately ended with a data set which contained the same amount of samples per each label. And once we had that, we did what I was speaking of before, which consisted of splitting the training, testing, and validation data sets. This now takes us to the actual model.
So we began our project by setting up TensorFlow, a powerful open source software library for machine learning. I highlighted the TensorFlow version and GPU availability to ensure compatibility and performance for our deep learning tasks. Next step was data preparation. We worked with a dataset consisting of facial images labeled with emotions, what Mono talked about, and the data was divided into the training, testing, and validation sets. We then transformed the pixel data from the CSV files into images and saved them into respective directories. This pre-processing step is crucial for the subsequent image augmentation and model training processes. After pre-processing the data, we configure our image data generators with augmentation options for a more robust model. Our model architecture leverages DenseNet 169 for feature extraction, followed by a series of dense layers for classification. We then proceeded with the training, initially freezing the DenseNet layers for a faster convergence in the first phase and unfreezing them later for fine-tuning. And after training, we evaluated our model's performance through various metrics and visualizations. We observed the accuracy and loss over epochs to understand our model's learning process. And using a confusion matrix and classification report, we could see how well the model performed across different emotions. Moreover, the ROC AOC score provided a comprehensive measurement of our model's ability to distinguish between the classes. Next.
Great. So now that we're done with model architecture and training, we will move on to the demo. Much like before, we will use data created in the user input program, namely face number 3, where I look pretty angry, as can be seen. Now, unfortunately, this model in comparison to the audio model isn't as accurate, as it predicts that I look happy, when in reality I don't. But nonetheless, it can be seen that we have a workflow established, which is in fact able to pre-process, or sorry, not to pre-process, but to process the image into input suitable for the model by setting image height and width parameters, ultimately saving this in the image pre-process variable and passing this in to the model.predict function, which, as I commented on before, predicts the wrong class, but predicts a class nonetheless. Now we're going to look at the read input file, and this is essentially a program which gets given a video path that is a file path to a .movie file. And once this is read in, the audio and visual contexts are separated and divided into both an audio.wav file used for the audio recognition, as Mesa did beforehand, and into .jpeg images, which are used in visual recognition, as I just showed. So now back to the PowerPoint, and we'll continue discussing our testing. So our test plan. So as can be seen, our functionality as of now has to do with model creation, implementation, and training. So all testing primarily has to do with performance metrics. The first one I'll comment on is accuracy versus number of epochs. And this is a graph that was shown beforehand where we saw how accuracy increased with the number of epochs, that is the number of training cycles that took place. We also have loss versus the number of epochs. And we know that our models are trying to constantly minimize loss, so it would make sense for loss to minimize as the number of epochs increment. Finally, we have a confusion matrix, which was commented on by Andres beforehand. And this essentially lays out the 3 other metrics seen under it and allows us to identify which labels are being predicted best, to concentrate on those that are being predicted worst, and enhance our model through fine-tuning.
Some other popular metrics to evaluate classifier models are precision, which is the ratio of true positive predictions to total number of positive predictions made. Recall, which is the ratio of 2 true positive predictions to the total number of actual positives present. And F1 score, which is the weighted mean of both and provides the most composite metric for evaluation.
On to part 3, issues.
So for the issues that we encountered and expected, first being model accuracy, although the model architecture and training processes follow a known standard, the accuracy for both models is yet to be as high as needed for reliable classifications. A solution to this was to localize shortcomings and fine-tune in reference to them. Another is training time. Part of the reason why fine-tuning has been a problem is that the model training times are high, so it takes a while to see results. And a solution to this was to utilize CPU memory more efficiently to expedite training processes. And recently, we actually were able to get a GPU, one of our strong GPUs, to use the CUDA architecture so that we can cut down training time significantly. Another process or problem that we encountered was the handling of large files. And we found it difficult to consolidate our code because of the large files that can't be uploaded to Git. A solution to this was to just use the git ignore files and store files locally with matching directory structures. And lastly, AWS hosting. Since we are still fine-tuning the models, we still aren't exactly sure which service plan would be best for us, although we have narrowed down our options.
Great. Now on to part 4, individual responsibilities.
So my individual responsibilities, I'm working on the user interface development. I'll be using the Python web framework to link backend functionality to functional and user-friendly frontend. And I'm also going to be working on the speech Q6 model.
I'm personally working on feature extraction, and although I've covered this throughout the past few weeks when it comes to the creation of both models, it's something that I'm still working on in hopes of fine-tuning the models and making them as accurate as possible. The user input program, which we've already created, has to be linked to the front end, which we're yet to implement, and I'll also be taking care of that. And finally, the facial expression model, I'm working on the architecture as well as post-training model correction, which, as I commented on beforehand, has to do with feature extraction and encompasses tuning the model to increase its accuracy and other metrics of correctness.
I will be doing the exact same thing for the audio model, same with the architecture and the fine tuning. I've also done the pre-processing and data exploration, as mentioned previously, and I did some of the research for the AWS hosting and will be continuing to find the perfect AWS service for us going forward. And that concludes our presentation. Thank you very much.